In section 6, we are going to take a look at applications of exponential equations. So exponential equations occur quite often in the real world as any situation where a quantity grows or decreases by a set percent each time. So that's what we're going to focus on here is percent growth and percent decay. So we're going to start with exponential growth. So our exponential growth equation is y equals a parentheses 1 plus r to the x, where y is our final amount, a is our initial amount, r is our percent increase as a decimal, and x is our time. And time here can be in any measurement of time. It just depends on the problem. So for our first example, we have that in 1985, there were 285 cell phone subscribers in the small town of Centerville. The number of subscribers increased by 75% per year after 1985. How many cell phone subscribers were in Centerville in 1994? So we're going to start with writing our equation. So we're going to have y equals our initial amount, 285, and then in parentheses, 1 plus, and it increased by 75%. So 75% as a decimal is 0.75, and then our exponent x. So now I want to plug in a value for x because I want to know how many cell phone subscribers were in Centerville in 1994. X here is going to represent our number of years after 1985, since the 285 is based on that year. So from 1985 to 1994 is 9 years. So we're going to do y equals 285, and then 1 plus 0.75 is 1.75, and then in my exponent 9. And I want to plug this into my calculator all in one step. I don't want to do 1.75 to the 9th, then round it, then multiply by 285. Just do it all in one step. And we're going to get y equals 43,871.99. Now, we can't have a decimal number of people, so we are going to round up. So there would be 43,872 subscribers. Our second example says the foundation of your house has about 1,200 termites. The termites grow at a rate of about 2.4% per day. How long until the number of termites doubles? So previous example, we were given a measurement of time, we solved for a future value. But we could also have a future value and we would need to solve for the amount of time, which is what's going on here. So I'm going to start off with writing my equation. So y equals my initial amount, 1,200, and then 1 plus 2.4% as a decimal is 0.024, and then my exponent x. And x here is going to be the number of days, because my measurement here is in days. If you are ever unsure on how to convert a percent to a decimal, you can always divide it by 100. So if I do 2.4 divided by 100, it will give me its decimal. So now I'm going to plug in my value for y. So we're looking for the how long until the number of termites doubles. So we're doubling our initial amount of 1,200, and double of that is 2,400. So we're going to have 2,400 equals 1,200. Go ahead and add, and we'll have 1.024, and then our exponent x. And we're now going to use what we talked about in section 4 to solve this exponential equation. So my first step is always going to be to divide by the initial amount on both sides. So 2,400 divided by 1,200 is going to give us 2 equals 1.024 to the x. Now to solve for my exponent, I'm going to convert to logarithmic form. So if you remember, Exponential form, y equals b to the x. Logarithmic form, log base b of y equals x. So we're going to have log base 1.024 of 2 equals x. And in order to evaluate that logarithm, we're going to use our change of base formula that says log base b of a equals log a over log b. And again, you don't have to show me that step. That's just what you're going to do in your calculator. And we're going to get, so we're going to do log 2 divided by log 1.024. And we're going to get that x equals 29.23 days. Now, I can have a decimal here when I solve for x. When you solve for your exponent x, you're solving for time. Time can be a decimal. It's not required to be a whole number unless it specifically states in the problem to round to a whole number. Otherwise, round 2 decimal places. And again, make sure you label your answer with units. So in this case, it's 29.23 days. Next, we're going to talk about exponential decay. So the only difference between exponential growth and exponential decay is that the equation is now y equals a parentheses 1 minus r to the x. So y, a, and x have the exact same definition as they did for exponential growth. The only difference here is now r is our percent decrease, but again, as a decimal. Other than that, same definitions. So for our first example, we have that during normal breathing, about 12% of the air in the lungs is replaced after one breath. Write an exponential decay model for the amount of original air left in the lungs if the initial amount of air in the lungs is 500 milliliters. How much of the original air is present after 100 breaths? So we're going to have y equals our initial amount, 500, and then 1 minus 12% as a decimal, 0.12x. Now this is a little bit different here because x isn't actually an amount of time. X here is our number of breaths. But it works the exact same way as an exponential function where x represents a measurement of time. So we'll have y equals 500, and then 1 minus 0.12 is 0.88, and then our exponent is going to be 100. So again, plugging this into my calculator all at once, we're going to get y equals, and because it's just a small decimal, I'm going to go 4 decimal places, 0.0014, and then our units are going to be milliliters. So not much of the original air is left after 100 breaths. For our second example, we have that you drink a beverage with 120 milligrams of caffeine. Each hour, the caffeine in your system decreases by about 12%. How long until you have 12 milligrams of caffeine? So we'll have y equals 120, and then 1 minus 0.12 to the x. X here is going to represent our number of hours. So we're looking specifically until we have 10 milligrams. So we're going to have 10 equals 120 and then 0.88 to the x. So solving for x works the exact same way for exponential decay as it does for exponential growth. My first step is going to be divide by 120. Now, 10 divided by 120 is not a nice decimal. So when that happens, we want to leave it as a fraction in simplest form. So 10 over 120 becomes 1/12 equals 0.88 to the x, which when we convert to logarithmic form becomes log base 0.88 of 1/12 equals x. So using change of base, we'll do log 1/12 divided by log 0.88 in the calculator, and we'll get that x is 19.44 hours. The last thing we're going to talk about are financial models. So something very common that is represented using exponential functions are something called compound interest and then something called continuously compounded interest. So the compound interest formula is A equals P parentheses 1 plus R over N to the NT. There's a lot of variables going on here, so I'm going to explain what each of these mean. A is going to represent our final amount. P represents our principal amount, which is just a fancy way of saying initial. R is our interest rate as a decimal. N is the number of times interest is compounded in a year. And then T is our time, and in this case, it is always in years. Unlike when we do general exponential growth or decay, time can be any unit of measurement. Here, for compound interest and then continuously compounded interest, T is always in years. So before I move on to the next example, I do want to talk about N here a little bit. So N, when we say the number of times interest is compounded in 1 year, we're saying how many times are you going to make money in 1 year. So there's the common values of N that we're going to see in problems. So when you see the word yearly, that means N is 1. If you see semi-annually, N is 2. So other than yearly, you could also see the word annually. Annually/yearly both mean 1. Semi-annually, 2. Monthly is 12. Quarterly is 4. Daily, 365. And probably the least often one you're going to see is weekly, which is 52. But again, that's the one that you're going to see the least often. The other ones, annually or yearly, semi-annually, monthly, quarterly, daily, very, very common to see. The second type of compound interest we have is continuously compounded interest. So that means you are always earning money. You are never not earning money. So the equation is a little bit different. It's A equals PE to the RT. So you no longer have an N, which is nice. And the base number E is a number. It's 1.81. It's a non-terming decimal like pi. So that's the base number we use for if you're continuously making money. So instead of the 1 plus R over N, we're replacing that with E. And then our exponent, because you're not going to make money certain times of the year, we're replacing the N with our interest rate R. But A, P, R, and T mean the exact same thing they did for compound interest. So let's look at a few examples. So you deposit $1,600 in a bank account. Find the balance after 3 years for each of the following situations. So an account that pays 2.5% annual interest compounded monthly. So we have our initial amount, so P is $1,600 and T is 3, and that's going to be true for all of these. For this specific problem, I now have R is 0.025 because 2.5% as a decimal, and N is 12. So I'm going to plug that into my compound interest formula. So I have A equals 1,600, 1 plus 0.025 over 12 and then our exponent 12 times 3. And again, I want to plug this into my calculator in one step. I don't want to do it in multiple steps because then I'm likely not going to get an answer that is as accurate. So we're going to have A equals, and then because it is money, we need our dollar sign, and then $1,724.48. So unless told otherwise, you are always going to round your answer to 2 decimal places because it is money, and money goes to 2 decimal places. Our second example says the account pays 1.75% annual interest compounded quarterly. So P is still 1,600, T is still 3, R is now 0.0175, and N is now 4. So we'll have A equals 1,600, 1 plus 0.0175 over 4, and then our exponent 4 times 3. So that's going to give us $1,686.05. It is a good idea that as you are doing these problems, you practice plugging them into a calculator so you know how to do it when it comes to an assignment or a quiz. Third example says the account pays 4% annual interest compounded yearly. So P is still 1,600, T is 3, R is now 0.04, and N is 1. So we'll have A equals 1,600, 1 plus 0.04 over 1, and then our exponent 1 times 3. So we'll have A equals $1,799.78. Last example, the account pays 3.25% annual interest compounded continuously. So P is going to be 1,600, T is 3, and then the only other thing I need is R, which is 0.0325. Because I'm now going to be using my continuously compounded interest formula. So we're going to have A equals 1,600 E, and then our exponent 0.0325 times 3. E is a button on your calculator. If you have trouble finding it, please let me know. I'll show you where it is. So we're going to have A equals $1,763.86. When it comes to an assignment or a quiz over this, the work that you are required to show is the work where you show me the values you plugged into the equation and then the final answer. So the part where I identified P, T, R, and N is not required on an assignment or an assessment, but the part where I showed this is what I plugged into the formula, this is what it looks like in my calculator, is required along with the final answer. Right. Next example. How much money would be in an account yielding 5.3% interest compounded monthly if I deposited $900 in the account and left it there for 9 years? So we have our P is 900, our R is 0.053, N is 12, and T is 9. So we have A equals 900, 1 plus 0.053 over 12, and then our exponent 12 times 9, which is going to give us $1,448.59. Next, how much money would be in an account yielding 4.8% interest compounded continuously if I deposited $1,250 into the account and left it there for 6 years? So P is $1,250, R is 0.048, and then T is 6. So we have A equals $1,250 e, and then our exponent 0.048 times 6. That's going to give us an amount of $1,667.20. The last example we're going to do is solving for an amount of time to reach a specific amount of money. So $12,000 is invested in a savings account yielding 8% interest compounded semi-annually. How long until the money is triple? So we have our initial amount, $12,000. We have our R of 0.08. N is 2. But instead of having a T, I now have an A. So I'm tripling 12,000, which is going to give us $36,000. And the steps are going to be exactly the same as when we solve for our exponent for exponential growth and exponential decay. So we'll have 36,000 equals 12,000, 1 plus 0.08 over 2, and then our exponent 2t. It is a very common thing that I see that people forget the n in the exponent when solving for a future value. So make sure you include n with t when you're solving. So my first step, divide by 12,000. And 36,000 divided by 12,000 is 3. I'm going to go ahead and figure out what 1 plus 0.08 over 2 is, and it's going to be 1.04. And then my exponent is 2t. Converting it to logarithmic form, we have log base 1.04 of 3 equals 2t. Evaluating using change of base, we'll do log 3 over log 1.04, which will give us 28.011. That equals 2t. Then my last step is to divide by 2, and t is going to be 14.01 years. So when you solve for time for compound interest or even continuously compounded interest, t is always going to be in years. When we did it for exponential growth and decay, we had to pay attention to what it was in the problem, but for compound interest and continuously compounded interest, time is always in years. So please let me know if you have any questions about compound interest, continuously compounded interest, or exponential growth and decay.